So we just talked about thermal actuators, and now we're going to talk first about resistive sensors. So what are resistive sensors? Resistive sensors are devices that convert a physical property into a resistance change. That means that we're going to make a resistor and use the resistor to change a physical property. And we're going to show examples for a resistor to measure temperature, for a resistor to measure strain, and for resistors to measure magnetic fields. So first we look at temperature sensors. Temperature sensors come in two flavors, metallic ones and semiconductor ones. Metallic temperature sensors are basically a piece of metal, like a normal resistor, and you know that resistance is temperature dependent. You can see that in the formula here. So the resistance is dependent on the resistant R0 plus a factor A. This is the thermal resistance coefficient times the temperature change, delta T. Plus also higher order terms, but we're going to neglect those. This is going to be too small compared to this one. And how does that work? Well, in a metallic resistor, basically you have to see metal is like a sea of electrons, and metal consists of a lattice of positive ions in which the electrons move freely. And is the movement of the electrons through the metal can be hindered by the thermal movement of the ions. So the more the ions in the lattice are going to move up and down, the more the electrons are going to be hindered from moving, and the more resistive the material becomes. The more difficult it will become for a current to move through. And therefore you can use that resistance. We say it's a positive temperature coefficient. That means the higher the temperature, the higher the resistance. So the resistance becomes a measure of the temperature. Very simple. In semiconductor thermal sensors we're going to call thermistors. And in a semiconductor, conductivity works different than in a metal. In a semiconductor, conductivity works by minority charge carriers that move into conductance band. So what happens is that you have a band structure of energy structure. So you have a valence band where most of your charge carriers are. Then you have a forbidden zone, and at a higher temperature you have a conductance band. And what happens is that due to thermal excitations, some of the carriers here will jump to the conductance band, and so you'll have a few carriers here that are very freely to move through the different in the conductance band. And it's the conductance band carriers that really will determine the conductivity of the material. So now what happens is that the higher the temperature, the more energy there is available, and the higher the chances that, for example, minority carriers such as holes or electrons jump from the valence band to the conduction band. And so the higher temperature, the more carriers you inject, and the higher conductance you'll have. So we say we have a negative temperature coefficient. That is because the higher the temperature, the lower the resistivity. So a negative temperature coefficient. Also, this effect is not going to be linear as in a metallic one, but it's going to be an exponential feature. So we see that the resistivity in function of temperature will be an R0 times an exponential factor. So we have a first quiz question now. Which of the below statements are true? 1. The resistance of a metallic temperature sensor changes rather linearly with the temperature. Or 2. The resistance of a thermistor changes rather linearly with the temperature. Or both are true. Or none is true.